Welcome to Schweitzer Drive, a podcast where we explore what goes on between the generation of electricity and the light switch. Join Dave Whitehead as he interviews the entrepreneurs, innovators, and experts who are inventing the future of electric power.
As the demand for clean, efficient, and sustainable energy continues to rise, will hydrogen be a key to a greener future, or will it remain a far-off dream? Today, Dr. Jacob Leachman joins us to share his expertise on the topic and break down the benefits and challenges. He's an associate professor in the School of Mechanical and Materials Engineering at Washington State University, where he initiated the Hydrogen Properties for Energy Research, or HYPER, laboratory. That's kind of a fun name. We'll get back to that in a second. The HYPER laboratory remains the only U.S. academic laboratory focused on advancing cryogenic hydrogen. Dr. Leachman has a BS and MS in mechanical engineering from the University of Idaho, and his master's thesis has been adopted as the foundation for hydrogen fueling standards and custody exchange. He also completed his PhD in the Cryogenic Engineering Laboratory at the University of Wisconsin-Madison and received the Roger W. Boom Award for Cryogenic Society of America in 2018. Jake, thanks for being here, and let's jump right into this.
Good morning, Dave. Thanks for having me.
This is going to be exciting, right? There's two potential future clean energy fuels that get me excited. One of them is fusion. Right, there's been a lot of research going on, and the other one is hydrogen. Maybe it's lesser known cousin, but this is going to be an interesting podcast. I've been looking forward to this one. So you're a local guy, and local being local to the Pullman, Washington area. And in doing our research, we discovered that you're lovingly referred to as Hydrogen Jake in the community, which is awesome. Could you please share a little bit about your background and what led you to your interest and expertise in hydrogen?
Yeah, sure. Well, it started in Lewiston, and let me say, when I grew up in Lewiston, it was a lot harder to get access to high tech than it is now, thanks to the SEL manufacturing campus and the Schweitzer Education and Training Center down there. So, big thanks for that. Yeah, being in Lewiston, you're around clean water. You get the clean electricity. You also see agriculture around us all the time. And, in the Pacific Northwest, we're the aerospace hub of the world, right? So, having those four key resources here was kind of embedded in my upbringing. And so when I went to Idaho and was in the engineering dorms and became close friends with many of the farmers in the area, they introduced me to a key problem that the area runs into. And that is all of our hydrocarbons, all of our fossil fuel resources we depleted them all in the 1960s. And so from a farming standpoint, if you're wanting to get fuel to run your farm or fertilizer, those all have to come and be imported in the region from faraway places. And so we're kind of stuck playing this game of taking whatever price we can get for our fuel and fertilizer to make our products. And then those food products we produce, we're stuck taking whatever price people are wanting to pay for them. And so this is kind of a tricky problem, but you'd think with all of our clean energy and water resources and everything we have here, we'd be able to solve this problem in some kind of way that's of benefit to the area here. And so when the National Institute of Standards and Technology needed somebody to develop new property models for hydrogen, which you can make from water and electricity, I was all in. So that was my master's thesis, where I had to go through and get all the properties of hydrogen that everybody's ever done. And one of my friends said, dude, you're literally shaping the surface of hydrogen properties with your mind. And that's when Hydrogen Jake came in, and it's stuck ever since. And so I'm okay with that. Hydrogen's 90% of mass in the universe. It's 62% of the atoms in our bodies. And when I was doing that research, realized there are all these really cool, literally quantum properties that nobody's ever gone in and tried to engineer novel devices and systems with. And so that became my goal. And I came right back to the area as soon as I got that training in cryogenic experiments and set up the Hyper Lab. And we've been doing it since 2010.
And what specifically is cryogenic hydrogen versus, normal hydrogen?
Yeah, so hydrogen it doesn't like other molecules or other hydrogen molecules. They don't like to attract each other very well. And so to make hydrogen very stable, you have to get it very cold. I mean, we're talking minus 420 degrees Fahrenheit cold. It's close to absolute zero.
What's absolute? Minus 272 or something like that?
Well, that's in Kelvin. Yeah. So in Kelvin, we're 20 Kelvin. So we're only 20 Kelvin away. Yeah. So we're like, 15
pretty
times
damn cold
of the way to absolute zero. Yeah. And when you think about liquid hydrogen and its density, to get the same density hydrogen at room temperature where we're at right now, you'd need to pressurize the hydrogen to 22,000 PSI. That's huge. And so you start to see why we like to distribute cold hydrogen and why 90% of all the small merchant hydrogen in the country is distributed via cryogenic liquid tanker truck.
How now we're gonna get a little off topic because now I'm interested. That's pretty dang cold, right? So how do you I like on large scale, or if we're talking we want to use hydrogen throughout the U.S. economy and stuff like that, how feasible or efficient is it to keep stuff that cold?
Yeah, that's where the biggest opportunity is. The big liquefiers, and there are about 12 of them running around the country right now. They all use 1960s technology. We literally set these up back in the wet fusion weapons days and the space wars days, and we haven't had any incentive to improve this technology since then. And so now that we're starting to look at hydrogen being able to do some of these clean and other energy uses, we're suddenly now trying to recreate the workforce and everybody needed to start engineering these systems. And so, in my lab, that was actually the thing that allowed us to become this first cryo-hydrogen lab. Until about 20 years ago, to do any kind of research with liquid hydrogen, you need a 16,000-gallon tank sitting outside your building full of liquid hydrogen. And that is a huge safety and cost burden that just precluded almost anybody from doing any kind of research into it. But about 20 years ago, they invented it's kind of like a Keurig for liquid hydrogen. It's called a cryo cooler. And, you plug it into the wall, you press the on button, and it'll slowly make a cup of hydrogen that's big enough to put a probe in and do research with. And so that's the big thing that's changed, that's allowing, everybody to start researching this finally again and getting the workforce developed.
Interesting. It's been said that hydrogen is the fuel of the future, and it will always be just that in the future. Can you talk about the challenges that prevent us from using hydrogen as a major source of energy in the here and now? And how can we overcome whatever the challenges might be?
Yeah, that's a great question, Dave. And so let me return a question back to you.
Okay.
Do you have anything on your person from Amazon or Walmart?
I bet the answer is yes. I just can't think of what it is right now.
Most people, if you go into a room, you get the majority of people in the room have something from one of those two outlets. And the neat part is all of their fulfillment centers that get the products and send them en route to you or store are all ran by hydrogen fuel cell forklifts by a company that has two offices here in Eastern Washington, Plug Power, with offices in Spokane and Colfax. And what the staggering statistic that I wish more people knew is 30% of the nation's groceries right now are moved with liquid hydrogen fueled forklifts. And when you think about that, hydrogen fuel is very much here now. It's just behind the scenes, kind of like a lot of SEL equipment operating reliably, and so you never even know it's there. One
of the challenges, as I recall from say doing fuel cells and what have you, is that proton exchange membrane, right? That's like the key, the magic is it. And this has been, 10 or 15 years since I really looked into this. We were working with a company up in Spokane on maybe commercializing that technology. But that was always the stumbling block, right? They'd either get plugged or clogged, or they weren't as efficient as they needed to be. What's the state of the art of that?
So it's improved incredibly. It hasn't improved as fast as batteries. The amount of money going into batteries has been much higher. But hydrogen fuel cell technology has improved. When I looked at the numbers 10 years ago, over 10 years, they decreased the amount of platinum a factor of 6 times. Their longevity is comparable to diesel engines in service for like buses and other things. And so that's one of the reasons why you see all of these forklifts running reliably on this fuel cell technology. I want to say Plug Power's made something like 40,000 forklifts now. So this is mature technology. It's out there. It's doing a lot of heavy baseload kind of technology. And the inverse of that too, not just fuel cells for producing electricity, but electrolyzers that take electricity and produce hydrogen. That's also really becoming mainstream. The amount of electrolyzers the world is building right now is outpacing the increase in solar and wind power installation year over year from the same starting point. So we're actually ramping faster than those did for hydrogen production equipment. So it's kind of a really exciting time with the cost coming down and the production ramping up to bring the cost down even more.
Is there a race then between batteries and hydrogen? And if there is, who's gonna win this race?
Yeah, so everybody wants to ask is it's one or the other, and the reality is almost all your hydrogen fuel cell equipment have a small battery in there. So the race and the competition standpoint is really coming from the battery world, where they're very afraid about losing some of their big market share. The fuel cell folks, yeah, we all need batteries. Batteries are great. Okay. But like with most things, the problem becomes people using a tool when it's not the best tool for the application, right? And so batteries have a lot more weight to get the same amount of electricity out. They're very heavy. And when you compare that to hydrogen, which literally is just a proton and electron, it's literally the lightest energy form in the universe. You can see there where the two can have a synergistic role to play with each other. One of the technologies that I'm most excited about is actually does both. It's called a battleizer. It's an old Thomas Edison iron water battery. And the problem with those old Thomas Edison batteries was once they were full, they started creating hydrogen like crazy. And then you get explosions because they weren't built to handle the hydrogen. And so some researchers around the world are making battleizers now that charge up, and those iron batteries are just totally indestructible, very durable. They charge up once they're full, then they design them to start taking the hydrogen safely away, and then you can store the hydrogen for longer term or sell it for some other use.
It's almost like you're doing the equivalent of like a combined cycle generator, right? Where we take the waste heat and we use it to do something else.
Yeah,
right. Useful.
Yeah, batteries, they're really great for your day-to-day, your regular cycling, or something as small as like a person or a handheld drill. They're fantastic for that. But when you want to haul a massive amount of things over a long duration and need that vehicle turned around running all of the time, that's where the weight comes into as an issue. But then the second thing that people don't realize about the electric vehicle problem is the power transmission problem. Okay. To give you an example, here in our state, we have many companies building these huge heavy-duty vehicles. So PACCAR's making hydrogen fuel cell trucks. Daimler Truck North America in Portland, they're making liquid hydrogen
Freightliners around here too, right?
Yeah, exactly. And then we have First Mode. They're making the ultra-class Anglo-American mining trucks to run on hydrogen fuel cells. Then you have Zero Avia that's looking at airplanes. Okay, all of these freight and logistics vehicles that you need going all the time and you don't want to consume the payload of, that's the great opportunity for hydrogen. It's kind of ironic that we thought it was all about the cars because that's what we use on a daily basis. We don't see the trucks that we're actually using on a daily basis to get all of the goods and services we need.
Both, whether it's the cars or the big trucks, suffer from one of the challenges I see with batteries are, and I make this probably bad analogy or this point is I have an F-150. Love that. It's a gas powered truck. And the reason I really like it is one, it can pull a lot of stuff. But the other thing is I can go 600 miles, right? And in 15 minutes later, after I fill up again, I can go another 600 miles. And right now I can't do that with a car, right? It's like I can only drink so much Starbucks and I can only answer so many emails, right? At a recharging station, right? And what does hydrogen suffer that same thing, or can I treat it more like filling up my gas tank, at the Safeways or wherever I might be?
Yeah, exactly. So Ford, just a couple of months back, came out and said publicly that they will never be able to make an F-350 run completely off of batteries alone. If they did make an electrified F-350, it would be totally hydrogen. And related to the fueling of the vehicle, yeah, absolutely. So right now there are 40 hydrogen refueling stations operating in California. They've been running for over a decade like that. One of the neat things about hydrogen, when you're filling one of these heavy duty vehicles, you're getting about 10 kilograms per minute. So a kilogram of hydrogen is about the same amount of energy as a gallon of gasoline. And so when you think 10 kilograms per minute of hydrogen, that's about 20 megawatts of energy transfer into that vehicle, which is enough to run small cities like the size of Pullman. Okay. And so when you look at that 20 megawatts, that's 100 times faster than even the biggest supercharger electric vehicle chargers that are out there. And that's one of the key things. Everybody's talking about making batteries lighter, and that's great. We want lighter batteries, right? But we still have the whole power transmission problem if you're just transferring electrons into those vehicles. And that's one of the ways where hydrogen can come in. It can actually help make our electric grid a little bit more comfortable, let's say, a little bit more reliable, and give us that ancillary ability to make electrons to balance the grid in the future, or fuel trucks, or make clean molecules and fuels, a number of different things that you can do with that hydrogen.
One of the things I've heard of this, perhaps the Achilles heel though of the hydrogen, is how do you create it, right? What is the unit cost per kilogram, or I don't know, gallon, whatever that unit equivalent is, right? Do I got to pour, I don't know, $100 in to make one gallon of liquid nitrogen or helium, excuse me. Hydrogen.
Everybody, it's literally something in our brain. I'm convinced everybody says nitrogen instead of hydrogen.
Yeah.
The amount of
I don't know why I did that though. I know what we're here to talk about.
I've been doing it for 20 years now, and I still do it. Okay.
Yeah. So, what is it about nitrogen then? I don't know. That's another topic.
It's like the air we breathe or something. Yeah. So the cost for hydrogen right now is completely. So let's talk about green hydrogen, the kind of hydrogen that we can produce from electrons and water here in the state of Washington, right? It's totally dependent on the cost of electricity. And the cost of electricity in the state of Washington can actually go negative if the wind is blowing, the water has to flow through the dams and everything at the same time. And so this brings up one of the most exciting applications that I've seen for hydrogen here in the region. For producing it. And it's not something that people would assume. Everybody thinks we're going to be losing our land and our water to producing hydrogen. And that's not necessarily the case. So the case that I really like is Douglas County Public Utility District. Okay. They're over by Wenatchee. They're their own balancing authority, meaning that they have to regulate the power on their electric grid within certain bounds, else the lights dim or electronics start breaking, that sort of thing. And they had a problem where when the wind was blowing and they had to flow water through the dams for the fish, they didn't have any knobs they could control to really balance their grid. And so what they were doing was they were ramping up their dam turbines up and down as fast as they could, and they were finding they were just destroying those turbines. When they went in and ran the numbers on the cost to repair these giant turbines that are bigger than the size of this room, they realized that if they had a knob that could take that extra power and just skim it off the top like an electrolyzer to make hydrogen with, that they could completely pay for the cost of the electrolyzer just in the reduced maintenance costs to their dams. And so Gary Ivory, who is the chief technology person for Douglas County PUD, told me that on top of that, just because they're able to balance that load and take that load when they need to, they get between $1 million and $1.5 million from the Bonneville Power Administration just for the ability to do that. And so they haven't even started selling that hydrogen yet, which is worth more than the electrons. That's all going to be icing on the cake for the members of the public utility. And so when you look at those hidden synergies in our electric grid, where we can start installing hydrogen to start shaving off some of the infrequent power peaks, like that, we can build out a major foundation for our freight and logistics sector just through balancing and improving the quality of our existing electric grid without having to take any new land resources or anything away from anybody else that way.
So that's a similar model, one would argue, for the batteries too. Let's charge batteries, right, when we have negative rates going forward. So I can definitely see the application then for generating hydrogen. One of the challenges, though, that let's call it grid scale batteries have right now, right? There's going to be a wear out cycle, right? You only can cycle them so many times before you're going to have to. Now, what do you do with all the leftover metals and everything else? Does hydrogen, could there be a grid scale hydrogen plant, and is it going to suffer similarly the way from a long-term perspective that the batteries do in terms of wearing out? Obviously, you got to change. Something's going to wear out, right? Because there is a chemical process going on. But what are your thoughts there?
So there's a lot of research that still needs to be done on how much the longevity of a fuel cell given how much, infrequent power you're driving to it. NREL, the National Renewable Energy Laboratories, they directly connected a wind turbine to a hydrogen fuel cell and found that it worked great for a period of several years, multiple years. Now, in terms of grid scale, the Douglas County PUD, they're going to have 10 megawatts installed, which is fairly significant, and that's just getting started. Fortescue and the Hydrogen Valley that they're planning over in Centralia, Washington, they're looking at 200 megawatts of installed capacity.
Batteries you usually do, megawatt hours kind of stuff, it's typically 10, for 4 hour megawatts hours seems to be like the scale. How do you do a hydrogen facility, right? Is there a limit to like a battery has on charge?
Yeah. So the convenient size for hydrogen is a liquid tanker. Okay, that's what it fits down the road. You can fit it under the interstate. That size cylinder is what you want to park on facilities for storing hydrogen. And a full liquid tanker is about 4,500 kilograms of hydrogen, and that's about 90 megawatt hours to give you an idea of stored electrons, a giant bucket of electrons sitting there. It's just the problem, and the reason we're not doing that right now, is that cold hydrogen you have in there is continually getting a little bit of heat. That heat boils the hydrogen, and then the pressure in the tank goes up. Then to keep the tank from overpressurizing, you have to vent some of that hydrogen. And so the existing facilities that are out there lose about 10 to 30% of the hydrogen just through that boil-off problem. But the neat thing is, and this is one of the things that we're doing in the focus of our research in the Hyperlab, is you can make coolers that just through solar panels about the same size as that cylinder that can completely eliminate that boil off, just providing cooling. And so, but right now the coolers are just slightly too small, and the big liquefiers are too big. They don't scale down well. So there's this window of opportunity for technology development in there that if we get those coolers that just with that solar energy like that can eliminate boil off, then you're going to start seeing everyone from data centers to hospitals, everywhere. They're going to have a giant bucket of hydrogen sitting there just ready if they need dispatchable power very quickly.
That's pretty cool. That's pretty good energy density, if you will.
Yeah.
I like that. Will you talk a little bit about your work you and your students are doing in your Hyperlab?
Yeah. So one of our mottos for the lab is we work with hydrogen safely so that others can too. And so we completely focus not on the generation of hydrogen standpoint. There's a bunch of research labs around the country that do that. We primarily focus on the logistics problem. Okay. How you just transfer and distribute and store that hydrogen to get it from one place to another. Because once we start having all of these electrolyzers coming online, which is what the plan is, that logistics problem comes shortly thereafter. And that's where, like I said, that 10 to 30% losses of hydrogen, we have a lot of opportunity for improvement there. And we have a lot of opportunity just to improve the efficiencies of those 1960s liquefier technologies and cycles. They're only operating at 30% of what is theoretically achievable, and they can't ramp with the renewables like we need them to. And so that's where there's a huge opportunity for technology innovation. And finally, we're starting to get the federal funding agencies interested in looking at some of these hydrogen storage technologies, because until recently, they said we don't have anybody qualified to review proposals in this area. Mm-hmm. So, that's finally everything's turning that way where, for the benefit of our region, where we can start making those hydrogens for whatever you want to use them for here locally using the abundant resources that we have.
What about the PACCARs or the Freightliners or those people? Are they dropping a lot of money in this? Or?
Industry has been amazing in this, and they're really the people pushing this. So in our state, I obviously can only talk about so much, but Microsoft gave us a big gift just to look at liquid hydrogen storage for their data centers recently. And all of those freight and logistics, those heavy vehicle sectors, everybody's starting to look into this. But the problem is, since we haven't been doing research or anything in liquid hydrogen forever, and only a few companies have been distributing that liquid, is that there's a giant workforce and training deficit. So a lot of professional engineers are out there and being asked to start designing hydrogen systems, and they might have some fuels background, but hydrogen is an entirely different rule set. One of the experts, once told me that hydrogen's no better nor worse than any other fuel. You just have to know the rules for working with hydrogen, and those rules are different. And so one of the things we're trying to do in the lab is we're trying to develop an entirely new training sequence. There hasn't been a textbook on liquid hydrogen written in over 30 years. So there's really a need for getting that knowledge out there. So we're writing a new textbook right now. We're also developing an online asynchronous training course that people can take through WSU's global campus. But you wouldn't ever want to trust someone designing a hydrogen system just because they took an online course, right? So those are the prerequisites to coming and doing an in-person week-long workshop series with us, where you get hands-on, learn how to do all of this safely and reliably.
Excellent. Got a lot of takers?
Yeah, actually, trying to estimate the demand for this, everybody's like, we need everyone trained in this. I mean, just to give you an idea, Blue Origin here in the state and the aerospace industry doing the liquid hydrogen rockets, they're having the same problem trying to retrain people as well. And they have thousands of engineers working there, just like Schweitzer has, many, many engineers that are trying to get retrained with this skill set. And so there's going to be huge demand for that.
That's excellent. All right. Time to be the great Karnak, if you will. What are the next steps you think will need to be taken to get us to a hydrogen world?
Absolutely. This is the, let's say, $1 trillion question that everybody really wants to hear, right? So the first step is we have those hidden synergies in our existing electric grid where having hydrogen installation will help make things better. And it's not an either or, batteries or hydrogen. Like the Battleizer shows that there's actually benefit for both, right? And so just developing and improving our existing infrastructure to have that hydrogen capability, that's the first step. And we can build out a solid foundation for our freight and logistics sector that way. But that isn't enough to totally displace our need for fossil hydrogens in the region. You can look at the numbers the Washington, government has those all populated. If you want to displace all of our importation of fossil hydrogens, you have to go offshore. And when you look at our offshore wind resources we have way off the coast, they're more than enough to displace our importation of fossil fuels. And what's neat is they now have electrolyzers that can take seawater directly and make hydrogen from that. You then just need some kind of cooler that sits in the column of that wind turbine, like what we want to try to develop, that just bottles that cold hydrogen, and then you can come in and bring it on shore. And then you're not adding more infrequent electrons to the grid or anything like that. You're just bringing in lots of hydrogen that can run a number of different things from wind turbines that might even be below the horizon. You can't even see them from the coast. And so that combination of things, once we have that going, the lab goal is by 2050 that we can make hydrogen the fuel of choice, where not only can you get it faster, you don't have to worry about, pollution or harmful emissions or anything like that. And it might even be cheaper than anything else that's an option by then. And so that, I think, is a future that we can all be excited for, where we have this complement to our electric grid that can not only stabilize and help it perform better, but can put back on and return to the electric grid when we need it to. And that's one of the reasons why when I got started in this, I realized hydrogen might be the coolest fuel in the universe.
That's it.
And so
it's been around for a long time, certainly. Hey, Jake, this has been really, really interesting. I don't know if I can wait till 2050 to get back to you to see if your predictions come true. Maybe we'll have to get back together before that.
Thanks, Dave. Thanks for having me. It's been a pleasure.
Thank you for stopping by Schweitzer Drive. Join us again as we learn about, explore, and celebrate electric power. For more information about the show, please visit selinc.com/Schweitzer Drive.